So we're going to talk about ionic currents, which describes the movement of an ion across the membrane. Now we can describe this using an application of Ohm's law, which we can write out. That says that the ionic current, which we write I for current, ion, because we're talking about movement of an ion, equals the G ion. G stands for conductance of the membrane to the ion. That's really the way to think about it, is how easy is it for the ion to move across the membrane. So this would be affected by things like channels being open to allow the ion to go across. And then you multiply that by the driving force, which is the membrane potential, which we write Vm, minus the equilibrium potential, which is written as E ion. And the difference between the Vm and the E ion, that is what we call the driving force. And we can just write that as F ion, if we like. Now, there's three scenarios that we can think about that could be happening in terms of ionic current. One is, what if we had no net movement of the ion? Well, we can think about it through the equation here. What that would mean is that the I ion equals 0, and that would be if sort of two possibilities. One is the driving force of the ion equals 0, and that would mean that the Vm is equal to the E ion, right? So if the membrane potential is at the equilibrium potential for that ion, the driving force is 0, and there will be no driving force. Even if there's a conductance, it doesn't matter, there's no net movement. The other option is that there's the conductance of the ion is equal to 0. So there could be a driving force for the ion, but if there's no pathway for the ion to get across, let's say there's no channels or something like that, you're not going to have net movement. So those are the scenarios for net movement of an ion being 0. Now, what if we have a net inward movement? Now, in this case, we have to think about cations and anions differently. So the way this works is that if I have a cation, if the current is a negative value, and this is by definition now, for negative currents for cations, that means that the cation is going in. And this would mean that the Vm is less than the E cation. So when we take the difference, we get a negative number. If we are looking at anions, negatively charged ions, by definition, if those currents are positive, that's also an inward current. And so in this case, the Vm is greater than the E anion. Now, finally, we can have a net outward movement of an ion. And in this case, it's just the opposite. So by convention, if we have a cationic current that is positive, and that would mean that the Vm is greater than the E cation, we would get a positive value, and that means that the current is allowing the ion to go out. And then if we have an anion current that's negative, the Vm is less than the E anion. So you can see that the driving force really dictates the direction that the ion is going to move. And interestingly, you can see that on either side of the E ion, the current changes direction. So you can see, for example, for the I cation, when the Vm is less than the E cation, it's an inward movement. But then when the Vm is greater than the E cation, the direction reverses, and now you have an outward movement. And the same thing is true for the anionic current. On either side of the E ion, the membrane potential is on either side, the current reverses. And so that's why another name for E ion is the reversal potential for that reason.